Now, there are going to be more of these, but at least to get us started here, there are a couple that you need to work with. Oh, let's see, we talked about one other one. We talked about fill, didn't we? Which allows you to set up a memory location with a specific value in it. Related to this one, there's this one, which stands for block word. What it does is it sets up in memory locations. It does not allow you to put values into those locations, but sometimes you don't need to. Sometimes, well, we'll do a problem here in a couple of minutes as an example, where we are generating values within a program that we want to store in a particular location. Note that that's going to jump your line counter by quite a bit. You'll see that here as we write the program in a little while. It's kind of like setting up an array, kind of what it comes down to. The other one that we really need to talk to, since you'll now be writing in this medium, is the .n. People get confused about the difference between halt and .end. Remember, anything with that dot at the beginning is a directive to the assembler and will not appear in the final program. Okay, what the .end tells the assembler is there are no more lines for this program. If you put memory locations with labels on them after this for storing data, you'll never see them. They won't be there. Because when the assembler sees .end, it quits. That's it.
But
yeah.
But you can use memory locations after that, right, to store values?
Not after the .end.
I mean,
you can after the halt, but not after the .end. Now, let me modify that a little bit. You can use them, but you cannot put labels on them.
that's what I meant.
Yeah. Yeah. There are, because the .end disappears when your program gets into memory. And, you know, you can access anything down to where the system tells you you've got an invalid memory reference. If you start trying to mess up with any of the system routines, anything that belongs to the operating system, it'll shut you down. But yeah, you can go on dynamic memory allocation, basically, but you can't put labels on. Okay? Now, let's see if I can find that problem that I wanted to do here. But I didn't see it there. Okay. This is problem 7.24. We have this program 0. And R2, R2, 4. And we have a label here. Now, it says that, he calls it a program fragment, but it isn't really a fragment, it's a complete program, it'll run. It says it's intended to shift register 3 to the left by 4 bits, 4 places. It says it has an error in it, identify the error and explain how to fix it. In other words, it's a debugging problem. This thing isn't giving us the right answer, and we want to find what's going on. There's a kind of an art to this thing. When you got a really big program, it's pretty difficult to do. But something this short, you can do it actually by doing what we call desk tracing. That is, you just go through and you execute those instructions one at a time and see what happens. Let's see, we're going to be using register 2 and register 3, and that's all, right? Yeah. Now, register 3, this is the part of it that makes it a fragment. There's nothing here that gets a value into register 3 to shift. So we'll just put something in there. I'm not going to do the whole 16 bits. We'll just do the last 8 bits. Suppose we start with that. And I'll have to work up into the next hex digit to shift 4 places, but let's see what happens. The AND, we've worked with that one, haven't we? That basically just clears register 2. So we've got a 0 in register 2. Now add, that basically gets a 4 in there because we take 4 plus 0, puts a 4 in there. That could, of course, be done in a different approach, but that's okay. Now, remember that there are certain instructions that change those condition codes. And this would have set the Z bit because the result of that operation was 0. This one changes it. After this instruction, we'll have 0, 1, 0, because the result of that instruction was a 0. After this instruction, it's going to be 0, 0, 1, because add also changes. Okay, so branch if done, or branch if 0. It's not. So we won't. So we subtract 1 from register 2, and we add register 3 to itself. When you do that, that'll give us this number. this one was positive, the result of this one is positive. Now, this is an unconditional branch, so we go back up to here. What's it going to see? Well, it's going to see plus, so it won't branch. So we go ahead and subtract one, and then we, well, I won't do the add. The net result is that
It's gonna keep on going because it's only looking at R3.
it's what?
It's looking at R3 instead of R2. It's supposed to look at R2 for the 0 on the branch done.
Yeah, that's essentially what's going to happen here. You see, as we do our shift, now we branch back up to here, we decrement, we shift again. Branch back up, decrement again,
If you
add
were to
again.
switch the two add commands there in the loop, you would be okay, right?
Yeah.
Now, you see, here's the problem. As we go through this time, when we subtract that one, our things look like this. But now this changes it back, because every add instruction does it. And so, yeah, the comment is exactly correct. What we're checking up here, first time through, we were checking register 2. But now, because of this, we're checking register 3.
So if you flopped them.
So if you just swap these, it'd be okay. The key is that between an instruction that sets those codes that you want to look at in your branch and the actual branch, there should not be any instructions that change the condition codes. That's what you have to look out for.
Branches do not change the NZP, is that correct?
They what?
The branch doesn't change the NZP at all.
No. No. If you look on the inside back cover, the instructions that have a little plus sign after them are the ones that change the condition codes. Adds, ands, loads, and not. Those are the ones that change the condition codes. Everything else is not.
So you could have put a store after that, before the branch. Right,
Yeah.
and it wouldn't affect
It
it.
wouldn't affect it. But an add, an and, a load, or a not will change it. Okay? Okay. Any questions about that? That process of hand checking the code as you go through is pretty significant. Much more so in assembly language than in the high-level languages, but it requires a certain amount of discipline, because we have a real tendency as we go through it to say, well, oh, I don't want to go through all that detail. I know what this is doing. Because you may not know what it's doing. You know what you think it's doing. So you have to watch out for that. Okay, let's write some other code here. Write a program to find the first 10 terms sequence unit with I'm gonna blow your minds here, because everybody says, oh, the Fibonacci sequence begins 1-1. Well, that's the typical one. You can actually define a whole family of sequences that would be called Fibonacci sequences. The only condition is that each term is the sum of the two terms that came before. So typically, you see we start with 1, 1, and then 1 plus 1 is 2, and then 2 plus 1 is 3. I'm going to go change that. 3 plus 2 is 5, 5 plus 3 is 8, and so on. But let's do 2 and 3. Let's start with 3 and 4, just so that we get something different here. If I begin 3 and 4, then 3 plus 4 is 7, 7 plus 4 is 11, 18, and so on. It's also a Fibonacci sequence. Okay. We can write a program in C to do this fairly readily. We would declare an integer variable there, and we'll need an index variable. We could say, well, let's set A0 to be 3, A1 is 4, and then we'll say for I equals 2, I less than 10, I equals I minus 1 plus I minus 2. And that's really it, except for the I/O. Okay, that's the portion of the code that would actually generate all of them. There's a real advantage to, when you attack a program like this, to sit and do that as a way of organizing your thoughts and your approach to the problem. It's a divide and conquer thing. You know, if you just attack the problem right from the beginning in assembly code, you can generate some of the most unreadable, illogical, excessive statement type program. What you really want to do, whenever you're writing in assembly language, your objective should be compact code and efficient code. And one of the best ways to do that is to get your thoughts organized pretty closely to begin with. And if you begin this way, yeah, a reasonably competent programmer can actually generate assembly language code that's a little better than what the compiler would do, because the compilers have to look at very general kinds of situations. Okay. For example, one of the things that happens here is it sets up a memory location for I. Now, if I want to write assembly code, go down in here and increment that I, remember what I have to do. I have to fetch it out of memory, put it in a register, add 1 onto it, and store it back into memory. But as I sit down there and write assembly code, I can say, hey, wait a minute. I don't need to have that thing out in memory. I can use a register. And so the I++ is a single instruction instead of 3 involving 2 memory references, which are really slow. So that's, I'm going to say here, just as a passing thing, I'm going to put I in the register 4. Arbitrary choice, no particular reason for it. I'm just going to put it out there. A is going to have to be in memory. So. Okay, let's see here. So I'm going to do this sort of thing. As I get down here in my code, which I haven't written, I'll get down here to my halt. I'm going to say block word 10. Okay, that's my setting up the array. I've just allocated 10 memory locations. Okay. Now, I can get these first two done here pretty quickly. So let's start there. Yeah. We'll use something different just to be different here. Remember this load effective address thing allows me to load the actual address associated with the label A into this register. Okay. Now what I want to do is store a 3 into that location. Well, I can't store in immediate mode. I have to store from a register.
Do you just want to explain, I think I missed it, what the block ward does, just briefly, sorry.
We'll count down the memory locations, but basically what it does is it sets aside 10 memory locations. We're going to have a dot end after that, but we haven't gotten to it yet.
When it sets up the memory locations, does it start at the A location?
Yes,
So that would be the 0 index.
that will be the 0, yeah. But that, you see, is totally under your program control, whether you call that A0 or, you know, in Pascal, we used to be able to set up arrays to where we would index them from 100 to 150, or something like that. You can do that here. It all depends on how you actually reference that memory location. But in this case, yes, that's going to be my A0, the first location. I could go from 1 to 10. It's all how I want to do it. Okay, let's see. We got to get a 3 into a register. Well, okay. I've got a 3 now in that register, so now I'm going to store it. And the store format that I'm going to do is the STR, store relative. Register 1 is the thing that's going to be stored. And now the rest of this instruction, I need a base register, which is going to be register 0, and then an offset from that. Okay, so it takes the value that's in register 0, which is the address of A, offsets by 0 locations. In other words, I go to the first of these 10 words, and I store the contents of register 1 in that location. Now I need to get a 4 in the next location. Instead of working to reload, I'll just add a 1 onto what's in register 1, which is a 3. That gives me a 4. And then I'm going to store that one one word farther on. Now, as it turns out, that's kind of an awkward thing as we get down into the, our loop now. Yeah.
Could you explain how the store works? One more time?
Oh. Remember if we had, if we just have a store, ST, okay, remember how this works when I do this? What it does is it figures an offset from where I am to this memory location A down here. It adds that offset onto what's in the program counter and uses that as the actual address. That computes the actual address as to where it is. So that if your program is moved anywhere differently in memory, you don't have to change that. Now, the thing that's different with this one is that instead of using the program counter, it uses the register that you specify. And since I loaded that register with the starting address of my array, this puts it right in the first word in there. This puts it into the second word. Okay? It does not change that base register, just like this one does not change the program counter. It adds them, but puts that address someplace else. Not back into the program counter or the base register, either one. Is that helpful? See where we are here?
So it adds the base register to the 6-bit offset that you have.
Yeah, it adds it, but it does not change the base register. Yeah, register 0 is not changed by this 1. Again, if you go back to the whole data path business, what it does is it takes register 0, puts that on one latch of the adder, puts a 1 on the other latch, it adds them together, the result goes into the memory address register. And then uses that to store what's in register 1. That's the way it actually works. Now, this instruction here illustrates how you can use that thing as a kind of a subscript into the array, an index. It's not a good approach, though, as we get down into the loop. Because remember last time I showed you a way where you can go back and modify an instruction so that you can change that offset. That's kind of awkward. We'll change the base register instead. Now that's going to cost me one instruction here, but that approach is going to be better later on. So what I'm going to do is I'm going to change the address that's in register 0. I'm going to increment it by 1, and then we'll store the thing directly. Begin our loop. Well, I haven't set up my loop counter yet. What I have done is these two. I actually showed how this was going to be done, but I just erased it because it's got to come a little farther on. Okay, so to set up my loop, I've got to set my loop counter. Here's another interesting thing about compilers and the way they handle loops. One approach is literally to initialize your loop counter here And then at every pass through the loop, you do this check, see if it's less than 10. That gets kind of tricky with the limited assembly language that we have, because to see if register 4 has a number less than 10, you know, I'd have to do a subtraction, which involves a naught and adding 1 to get the 2's complement, and then add that because I don't have a subtract instruction. It gets to be a real mess. Instead of doing that, we'll figure what's commonly called a trip count. Some assemblers will, or some compilers will actually do that with these things because it's easier to work with.
It's called a trip.
Trip. We'll do a trip count. And as I can look at this thing ahead of time and know how many times I'm going to go through that loop, as long as it's a nice, simple loop like this one. Some of the others don't lend themselves to this very well, and particularly while loops don't. It's hard to figure trip counts on while loops because you don't know when that condition is going to fail. So, but in a nice for loop, you can look at that and say, well, gee, I've got to do it for 2, 3, 4, 5, 6, 7, 8, 9, 10. No, not 10, just through 9. We've got 8 trips to make through this loop. So now the easiest way to handle it is to put that trip count into the register and decrement it, and then you check to see if it's 0. That's an easy check. We just have the BRZ instruction.
Well, could you just start with the negative number and then add 1? And then
Start with -8 and add back up, yeah. It's not going to be any different, really. Yeah. You can add -1 just as easily as you can add +1. And as I get this initial value in there, I could add -8 instead of +8. Yeah, it'd be absolutely equivalent and would use the same number of instructions.
Did you initialize I in the for loop to 2? Is that a 2
Yeah.
that I see? Okay. That's why it's 8 trips.
Mm-hmm.
Okay.
2 through 9 inclusive. Okay, now, register 4, we need an 8 in register 4. Well, we've got this same trick. We clear it, and we add an 8. Okay, that sets up my count through the thing. Now, I also need to set up my addressing register. See, it currently has the address of A1. I want it on A2, so I will add one onto there too. Okay, now I'm set to do my loop. We're gonna make it? Probably not. See, here's some grief. Oh, but I can do that. I can do it. I can use the LVR instruction. Register 0 basically contains the address of AI. I want to go one back from that. Yeah, I can use a -1. now I've got these two things in there, I can add them. I don't need to keep them in here, so I'll just add register 2 and register 3 and put it into register 3. And now store the thing out, and because of this change, register 0 has the address of where I want to store it. So I'm going to store register 3 into register 0 with no offset. Now let me finish this loop and we're not gonna get all the way down to the end, but that's okay. I want to now get set up for the next pass through the loop. I do that by changing my address here, increment it by 1, and now my loop counter, which is in register 4, I will subtract 1 from it. Okay, let's play with that and trace it here for a moment. Well, let's see, for the time being, let's say that we put a halt here. And then immediately following that, we have A, which is block word 10, and then we have the dot end. Okay, so where are we? This is location 2900, 1, 2, 3, 4, 2905, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is 290F. Which one was that? 12, 13, 14, 15. This is 2911 here. This is 2912. Now, this one doesn't actually occupy a memory location, but if it did, it would be at 291C. That's what the block word does. That's the point. It jumps this thing up quite a little bit.
It jumps it by 10 locations.
By whatever you put out here. Okay? Now, typically, with assemblers on real-life machines, rather than this LC3, it doesn't necessarily begin with that memory all having zeros in it. And this is the source of your problem when you don't initialize variables. All it does is jump down to there, and whatever was in those 10 memory locations is still there. If you use .fill 10 times, you initialize everything to zeros. But just with a block, it just jumps over them.
Does that necessarily matter? Because all you're doing in this program.
In this program, it doesn't matter. You're absolutely correct. That's why I haven't fussed with it. But in general, if you have a problem and you allocate a bunch of memory and assume that there are zeros in there, you can sometimes get really weird results, because they may not be zeros. Okay, let's see what happens here as we make a couple of passes through this thing. We've got register 0, register 1, register 2, register 3, and register 4. And let's see, down here we've got 2912, 2913, 2914, cetera. We may or may not get down that far, probably not, since we got about 6 minutes here. Okay, what do? This says load the address of A into register 0. The address of A is 2912. Okay, be sure you understand how that load address thing works. It loads the address of wherever that thing is in memory. Okay, the AND instruction clears register 1. The next one adds a 3 onto it, so we've got a 3 in there. Now, this says add a 0 onto register 0 and store the contents of register 1 in that location. So register 1 gets transferred out here to 2912. Add 1 to register 1. 4. Add 1 to register 0. 2913. Now this says add 0 onto register 0, so I get 2913, and store the contents of register 1 out there. Now then, this clears register 0 and this puts an 8 in it. We add 1 onto register 0, so now we've got 2914 in register 0. Okay, now we get into that base offset addressing mode. As we begin our loop, it says add a -1 onto register 0, so that gives me 2913. Is load from 2913 into register 2. Well, 2913 is a 4, so I get a 4 into register 2. But it does not change register 0. Okay. Now this says add a -2 onto register 0, so now I get 2912. Go out to that memory location and put that into register 3. Okay, watch that offset thing. It adds it and uses that as an address, but it does not change the register. We've got to get through this loop one more time. Okay, we add register 2 and 3 together and put it in register 3, so now we've got a 7 there. Store, it adds a 0 onto register 0, which leaves me with 2914, and I copy register 3 into that location, 207, not 9. Add 1 onto register 0, subtract 1 from register 4. Register 4 is still plus, so we branch back up to here. Now, -1 onto register 0 gives me 2914. I load from that location into register 2. Well, there's a 7 out there, so I've got a 7 here. -2 on this gives me 2913. So I go from that location to register 3, that's a 4. Add them together, in decimal that gives me an 11. Store it, I add 0 onto register 0, 2915, and that's where I store register 3, 2915. 11. Add 1 on here, subtract 1 here, Okay, still positive, so now I loop again. And you see, as I go through here, this combination, since register 0 keeps changing down here, I'm constantly referencing different memory locations. -1 onto register 0 is now 2915. That's this location, so I load that into here. -2 gets me at 2914. So I load a 7, add them, 7 and 11 is 18. And then I store that in 2916. I hit my 18 out there and loop again, work my way through it. Okay? Well, we're out of time. We got 2 other things we need to talk about, but I guess we'll talk about them on Monday. Questions, quickly, since we're out of time.